Welcome back to The Explainer. I am absolutely thrilled to have you here today because we're going to unpack something truly phenomenal. It's something most of us literally use every single day, but we almost never stop to appreciate the staggering engineering feat hiding right there behind our screens. I'm talking about the digital map. Today, we're uncovering the massive, planetary scale architecture that actually powers our everyday route queries. We'll be looking at exactly how data, algorithms, and distributed systems all come together to draw that perfect blue line that gets you to your destination. Okay, let's dive right into this. What they experience as a simple blue line masks one of the most sophisticated distributed systems ever engineered. I just love this quote. It perfectly captures the massive contrast we're exploring today. On the surface, your experience as a user is beautifully simple, right? It's totally seamless. But just beneath that glass screen is an incredibly chaotic computational reality that is processing petabytes of data all over the globe. And to really wrap your head around this scale, just look at this number, 1 billion. That represents the daily active users. We aren't just talking about a system finding a single route for you. We're talking about a system that has to answer routing requests, search queries, and map tile loads for a billion people, all at the exact same time. It is a mind-boggling, truly planetary scale. To manage that kind of insane load without completely buckling, the architecture just has to be absolutely flawless. Seriously? Have you ever stopped and just really thought about the journey of a single map request? You whip out your smartphone, you type "coffee near me," and before you can even blink, you've got a perfect list of locations, a glowing blue route, and an exact time of arrival. How does that request travel thousands of miles to a data center, sift through billions of data points, and then beam a flawless answer right back to your screen in mere milliseconds? Well, let's start with part one, building a digital Earth. Look, before any searching can happen, the system has to undergo a pretty intense setup phase. You can't navigate a world that the computer doesn't understand. So the very first step is physically ingesting the real world to build a digital twin. And to build this digital Earth, the system is basically drinking from a fire hose. It's pulling in massive amounts of high-res satellite imagery, live OpenStreetMap edits, government datasets, and get this, a staggering 50 million GPS pings every single second. It's a massive data cleaning operation. The system has to standardize all this messy, real-world input, deduplicate it, and validate it just to create a baseline. Now, what's really interesting about this slide is how we solve the headache of organizing all that geodata. Because you obviously can't scan the entire globe every time someone searches for a latte. The solution here is spatial indexing. Older methods, like quadtrees, use square shapes, but they suffered from huge polar distortion. Then you have GeoHash, which uses rectangles, but that causes frustrating edge discontinuities, meaning two coffee shops right next to each other might end up in completely different database prefixes. The real winner here is S2Cells. They use curved quadrilaterals, have minimal edge artifacts, and store data as lightning-fast 64-bit integers. So what does this actually mean? To clarify, S2Cells basically project the Earth onto a six-sided cube, and then they use a mathematical concept called a Hilbert curve to subdivide the faces. The absolutely brilliant part of this geometry is that geographically close points end up mathematically close together as numerical 64-bit integers. By eliminating those weird boundary artifacts, your initial Coffee Near Me database lookup transforms from a massive search headache into a localized, lightning-fast integer scan. Moving right along to part two, drawing the map. Okay, so the Earth is digitized and organized. But how does that data actually end up rendered on your smartphone? The map isn't just one giant picture, it's broken down across 23 different zoom levels, going all the way from the whole globe down to a single building footprint. To draw this, the industry had to make a massive shift. Older systems relied on raster tiles. These were static, pre-rendered image squares. They were heavy, like 150 kilobytes each. And if you wanted to change the visual style, you had to re-render the entire thing. Modern systems shifted to vector tiles. These just send the raw geometric data and the styling rules. They're incredibly light, just 15 kilobytes. This switch saves a ton of battery and bandwidth, and it lets your phone's GPU draw the math on the fly. That's what gives you that incredibly smooth zooming and 3D tilting. Which brings us to part three, the routing revolution. We've organized the world, we've drawn the map, now we hit the really fun part. The user selects that coffee shop and asks for a driving route. This introduces a massive core conflict. How on earth do you route across a continent in milliseconds? Think about it. The global road network has roughly 1.2 billion road segments and over 500 million intersections. If you use traditional graph-solving math, finding a cross-country route explores millions of nodes and takes actual minutes to compute. For someone staring at their phone, that is obviously way too slow. Let's see how this builds and how we solve this. First, we had Dijkstra's algorithm. Now it's guaranteed to find the shortest path, but it's a brute force method. It's kind of like dropping a pebble in a pond. It ripples out in every single direction, which takes minutes on a large scale. Next up, A-star search improved things by using straight-line heuristics to give the search a directional cone, dropping the time down to about 400 milliseconds. But the ultimate algorithmic shortcut used today? That's contraction hierarchies. It only needs to explore about 500 nodes, giving us an answer in under 1 millisecond.
So why is this specific algorithm an absolute game changer? Well, contraction hierarchies basically pre-calculate the most important highway routes offline to create mathematical shortcuts. Think about how you actually drive. You don't evaluate every single residential side street between New York and LA, right? You just get to the nearest major interstate. The algorithm does the exact same thing. By skipping millions of local roads, it drops computation time from literal minutes down to under a millisecond. It beautifully solves the continental routing bottleneck.
But hey, driving isn't the only way to get around. If our user decides to hop on the subway instead, a standard graph search kind of breaks down because public transit runs on strict schedules. Instead, the system uses Raptor, the round-based public transit routing algorithm. Raptor is incredibly efficient. It scans time-expanded transit schedules round by round, so it can easily account for multiple transfers and walking segments without all the heavy overhead of traditional graph exploration. Now let's get into part 4, the living, breathing map. So we have this perfect route generated in milliseconds. But a perfect route on paper is absolutely useless if it drives you straight into a 5-mile parking lot, right? The map has to be a living, breathing thing. To adapt to reality, the system relies on a massive fire hose of live data continuously feeding into a real-time traffic pipeline. We're talking anonymous GPS data from active navigators, background apps, fleet and logistics vehicles, and even built-in OEM-connected cars. Add in all the live user incident reports about accidents or hazards, and you get this incredibly comprehensive, second-by-second picture of physical road conditions. So the crucial point is how incredibly fast this data actually changes your map. Trace this pipeline with me. First, data streaming platforms like Apache Kafka ingest the fire hose of updates. Then, processing engines like Apache Flink match those raw coordinates to specific road segments and aggregate the average speeds. Third, a high-speed Redis cache stores these live segment speeds. And finally, the routing engine picks this all up and updates the internal edge weight, or the computational cost of that road. From a real-world traffic jam to an updated mathematical cost on your route, that entire pipeline takes just 30 seconds. But predicting your exact time of arrival, that takes it to a whole other level. Because a traffic jam on a highway off-ramp doesn't just stay on the highway, it ripples out into the surrounding surface streets. To accurately predict your ETA in these constantly shifting conditions, modern systems use machine learning models, specifically graph neural networks, or GNNs. These models don't just look at isolated roads. They actually understand the complex congestion ripples across the entire road topology to give you a shockingly accurate arrival time. And finally, part 5, designing for failure. And this brilliantly illustrates how this whole chaotic thing stays alive. We have this immense system processing billions of queries, crunching massive algorithms, updating live traffic. How does it survive a peak event like a holiday rush or natural disaster without just completely crashing? The answer is 99.99. The system maintains 99.99% uptime, which is absolutely crucial because people literally rely on these maps during actual emergencies. It pulls this off by expecting failure from the ground up. Every piece of data is replicated. If an entire data center goes dark, load balancers seamlessly reroute your queries across globally sharded servers. You get your route in milliseconds, and you never even know that a server across the continent just completely failed. Which leaves us with this final, incredibly provocative thought to ponder. As these systems continue to ingest more and more live data, as they map out 3D lanes, and as they begin to guide fully autonomous cars with centimeter-level precision, where does the digital world actually end and our physical reality begin? The map isn't just reflecting the world anymore, folks. It is fundamentally shaping how we interact with it. Thank you so much for exploring this incredible architecture with me. Keep wondering, keep learning, and I'll catch you on the next explainer.